Yeah, I want to talk about inverted F antennas and how I typically design them. These antennas are pretty useful because you can put them at the edges of circuit boards. They're pretty compact and they're very easy to tune. So if you start with a monopole, and there's a couple alternate ways of looking at this, but this is the way I tend to interpret the inverted F antenna. You start with a monopole. It's typically going to be a quarter wavelength long approximately. It's above a ground plane or a counterpoise, I like to call it. You're feeding it with a small voltage source right here. You look at the equivalent circuit of this before, from DC up to resonance, you have a resistance, which is comprised of a radiation resistance and a loss resistance, a lossy resistance of the finite conductivity material. So as this thing moves up in frequency, and at low frequencies, you're going to start off, this inductor is essentially not going to be there. You're going to have a lot of capacitive reactance. So you're going to start here at the open circuit on the input impedance. And as you go higher in frequency, this eventually resonates and you hit resonance, so you have a total real input impedance. And as you go higher in frequency, you're going to have a inductive reactance for your input impedance, and it goes back to the open, eventually loops back around again when you hit the second resonance on the thing. But if you look at the input impedance of this thing, you have a very low impedance right here and a very high impedance up at the tip. You have a lot of current down here near the bottom and very high voltage up near the top. Now if you take this monopole, you can take and form an inverted L because it looks like a sideways L. Take and bend this thing over, and when you do that, you end up with the near fields reflecting off the ground plane or the counterpoise and coming back up, and you have sort of a transmission line type effect, a very short transmission line. And we're going to keep the exact same length as before, but just fold it over. So when you have that short transmission line, where it's much, much shorter in a wavelength, you have an equivalent inductance that you can put in parallel with the equivalent circuit. And when you do that, you have the resonance right here. It is eventually going to come down and get to a short circuit. If you decrease this distance, you're going to come down and hit a short circuit. Equivalently, you're also adding capacitance, shunt capacitance from the pole right here down to ground, and that's going to increase, so you can follow this way. But the effect is that you're going to decrease the overall input impedance, which means your radiation resistance is going to go down. Your real resistance is probably going to be about the same, but if you have a decreasing radiation resistance and a real resistance that stays the same, your total efficiency is going to go down. You're going to be inducing currents in this copper down here, and that's going to kill some of your efficiency also. But what you can do, since your input impedance is very low now, the closer you bring this to the ground plane, you can take and drive the thing from an offset. Up here I was talking about a low impedance input, a high impedance input. So if you take and imagine shunt feeding the thing, I think gamma feeding it is what it's called, gamma match, feeding it at a point right here, you can raise the input impedance. Some people describe it also as you have added capacitance right here. You can take and add this offset arm as a inductor right here, but you essentially get the same effect. If you're offsetting the feed, you're going to raise your input impedance as you drive the thing closer towards the open. You're also going to get some inductance right here due to this feed offset. But since this thing is electrically short, it's going to tend to be more capacitive reactance. Adding that inductance is going to help you with your match that you get right here. So you end up increasing your input impedance, but when you do that, you're still going to decrease your bandwidth. So your bandwidth is going to narrow up. Back here, if you had a very low impedance source you're driving this with, you could preserve bandwidth. But since we're going to want to drive this with, say, 50 ohms, you're going to lose bandwidth due to the fact that you're trying to impedance match it right into here. So I want to demonstrate this on a circuit board. It doesn't have to be at the edge of a circuit board. It could be, a bent wire over a ground plane or a flex circuit. I've done those too. There's plenty of ways to make this thing, but I'll start with a simple FR4 circuit board. I have a piece right here that is a scrap piece. So this stuff is 59 mils thick for the core, so 1.453 millimeters, and it's 1 ounce copper, which is about 1.4 mils for each thick layer of copper, or 35 microns, 0.035 millimeters. Dielectric constant of FR4 or G10 is approximately 4.5. This stuff can vary, between 4 and 5, so it's all over the place. It's not very good material. And it's very lossy. It has a loss tangent of 0.02, unlike most microwave materials, which are going to be below 0.01. And a 50 ohm transmission line on this is going to give you a width of about 2.7 millimeters. And there's only a couple of things we ought to keep in mind. A quarter wavelength. I'm going to design this for GNSS or GPS, so pick a center frequency of 1575 megahertz. So taking a quarter wavelength free space for that is going to give about 48 millimeters. And then the worst case electrical wavelength is going to be in the material. So that's going to be, divide that by the square root of the dielectric constant, you're going to get 22 millimeters. So the actual, since the antenna element is going to be sitting up, away from the copper, it's going to be sitting on top of the dielectric. You have that filling factor to take into account. So it's going to be more than 22 millimeters and less than 48 millimeters. But we'll use the electromagnetic simulator to figure out what the proper length of a monopole is, and then show the conversion to an inverted L and finally the inverted F to see how this thing evolves from a monopole down to the inverted F, and look at the impedances and how the bandwidth changes. So I've already got a microwave alphas project set up and simulated, but I'll walk through and show exactly how I did it. I use this type of setup a lot for 2-layer, 4-layer, 6-layer boards. So let me go through and show exactly what I have set up here. Options, project options. Since we're going to have a center frequency of approximately 1575, I'll start at 1 gigahertz and sweep up to 2 gigahertz, and then in 50 megahertz steps. But once we, around our desired resonance, which is 1575 megahertz, we're going to move in 5 megahertz steps to capture that resonance better. And looking at the units, we're in metric, of course, and frequency of gigahertz, and nothing out of the ordinary. That's all about it. Now, looking at the drawing layers. So by default in microwave alphas, you get a copper layer. So I've added a copper plus and a copper minus. And what happens when you draw something on copper plus and then draw something else on copper minus, when you do your processing rules, it's going to subtract copper minus from copper plus, then transfer that over to copper. So it's a very handy way of doing cutouts in material in the board or the copper without having to do a bunch of unions and stuff like that that can get very messy. So for copper plus, I've used the same color as copper, but I like to use a positive slope for the fill, and then copper will be a negative slope. There's ways of doing this where you can visually make them add and subtract, but I like to see all the layers, therefore I have the positive negative slope thing going. So copper 2 is going to be the bottom layer of the board. Again, same type of the fill, and then I'll change the color to something that looks, green for ground plane, I guess. And then same positive and negative slope going on right here. And I've done the same thing for the board. You get a board layer by default, and then I'll add a board plus and a board minus should we want to do the cutouts on the board. And I've added one more layer down here, which is the notes layer. When you add these layers, they'll appear at the bottom. I like to move them up, right underneath. And you also get model layers in there added by, when you add the drawing layer, automatically adds a model layer, and I'll move those up too. Now 3D, this is only used for 3D visualization. It doesn't have anything to do with the EM simulation, but nonetheless I like to have it set up so I can kind of see what's going on. And this is why I like to have this stack up drawing up here also. So if you look at copper, that starts at a Z position of 0, and it's going to be 35 microns positive thickness. It's going to go upward, be extruded upward above the board. Copper plus and copper minus are going to be the same thing. Where copper 2 is going to start at a Z position of negative 1.453. That's the bottom of the core. And it's going to go downward by 35 microns, and do the same thing for copper 2 plus and copper 2 minus. Not going to use any of the solder mask or leads or anything for this. The via hole is going to start at a Z position of 0 and go downwards through the core. It doesn't need to go through the copper. It can stop at where the bottom layer of copper starts. And then drill, that's not going to be used, but the same thing. And then board is going to start at 0 and it's going to have a thickness of negative 1.453, the thickness of the core. And the same thing for board plus and board minus. Now I've got the dielectric constant and loss tangent defined as variables. And I've added this microstrip substrate, even though I'm likely not going to use it. This defaults to 1 right here, the resistivity relative to gold. I've set that to 0.652. That's the resistivity of copper, relative to gold. It's better or lower resistivity. So in this project, we're going to be using 2 simulators, Axiem 2.5D simulation, Analyst full 3D simulation. 2.5D, it's going to be on infinite substrate. So you'll draw your metal layers and they'll be sitting on infinite substrate. The nice thing about this is very fast. The problem with the infinite substrate is you're not going to get very good radiation, far field computations for waves that are coming parallel to the substrate. So at theta equals 90 degrees, it's really not going to give you a decent pattern, if one at all. But you're still going to get a decent input impedance. You're not going to be able to account for the edge effect of the substrate. If your copper is right on the edge of the core and then it transitions to air, it's not going to be able to capture that. But it is going to be able to go a lot faster than the 3D simulation and get you, 80-90% of an answer. Now, if we look at this, I've added these variables in right here for the dielectric constant and loss tangent. When these stack-ups are brought over into your EM structures, this is actually going to be replaced with these numbers. So you want to go back in your EM structures and put these variables back in if you want to use it. Conductor definitions, that's the generic copper that's in there. So dielectric layers. So earlier on the piece of paper I showed that 48 millimeters was a quarter wavelength free space. So our boundary conditions are open at the top and the bottom. That's going to be 377 ohms per square. So with a wave, coming in orthogonal to that TM wave, it's going to perfectly absorb that. Once the wave gets at an angle, it's going to lose. It's not going to be, it's going to reflect slightly, but since we're getting this thing a quarter wavelength away, we're going to be essentially out of the reactive near field. So we're going to get a pretty good approximation to free space. We keep our boundary conditions a quarter wavelength away, just round it off to 50 millimeters. And the core is defined as the core thickness, which is up here, and is the material of core, which has been defined right here. Materials. I like this naming convention. I like to have Cu for copper, and then 1P0 for 1 positive, and then OZ for ounce. So it's going to be 35 microns thick, positive direction, and then made out of copper material. And then 1N0 for 1 negative ounce. So minus 35 microns thick of copper. And then I'll do the same thing for half ounce copper, 0.5 positive and negative. Typically on a board, you're going to start with a half ounce electrodeposited copper, and then when you drill your holes, you're going to need to plate those holes. So you're going to plate up by a half ounce. So the outers are going to be 1 ounce thick and the inners are going to be a half ounce thick. And this core sub, this is really more for use in Analyst, but I'll make a material called core substrate out of material core, the dielectric, and then give it a generic thickness of -1. You'll see in a second why I've done that. So EM layer mapping on EM layer 2, which is right here, it's going to be 1 ounce positive copper. Same thing for the plus and minus layers, but copper 2 is going to be 1 ounce negative copper on EM layer 3, and it's going to extrude downward. That's why we need to add a negative thickness to it. Via is going to start on layer 2, and it's going to go downward by 1 layer, and it's going to be half ounce copper because it's going to be plated, and then the board is going to be empty. So you can see the actual EM layer mapping. If I go back into here, I'll go ahead and define my EM layer mapping in the stack up, and then come back in here, and I'll take, and it will be called default, and I'll rename it. I'll rename it to Axiem, then I'll copy that over and change the name, new copy's name to Analyst. So we have the exact same thing, but the board layers are going to be different now, and I'll explain that in a second when we get the Axiem stack up. So again, this one uses Axiem EM mapping, and this one uses Analyst EM mapping, but they're both part of the default layout process file. Again, this is all the same until we get down to board. So the board is going to be made out, we're going to call it a via, so it's going to extrude down by one extent, one layer, and the material is going to be this core substrate. And back here, you can see the thickness doesn't matter here. We'll just call it generic -1. But this is going to extrude downwards now, and it's going to physically add the material in. So we have an EM structure which is all made out of air. We need to draw that board material. You go back in the dielectric layers. Now, instead of having a layer of defined as a core material, I'm just going to set everything to air. So we'll still have the same layer thicknesses, but everything is air, and the EM mapping will add that substrate material in for us. Now the rules, and these same rules are going to be used in this other stack up. This is for geometry simplification, to simplify the meshing. Max trace width, 2.7 millimeters was our 50 ohm line, so it needs to distinguish between what's a transmission line and what's dumb metal. The metal could be carrying currents, it could be a ground plane, but if we set this to 3 millimeters, this is going to tell that anything above 3 millimeters is going to be kind of dumb metal. Anything below that could possibly be a trace. Any vias that are connected to ground, we're going to reshape those to squares, so it's going to be 4 sides. Except vias that are connected to feeds or traces, and this is important why you have this trace width set. It's going to tell that to go to an octagon, so it's going to have better meshing for these. Remove via pads. If you have like an actual pad of metal above and below the via, it can remove those because they're really not going to add. It's going to try to mesh that, and it's not going to get you anything accuracy wise, so we'll try to remove those small pads on top of the vias, and then merge via. So if you have, let's say, a via stitching or via shielding, any vias that are closer than a radius of 2 times via diameter, it's going to merge those together into a wall. So if you have a long thing of shielding vias, it's going to turn those into a giant rectangle. Or if you have a shielding wall, it's going to turn those into a solid wall of vias. Since we're going to be looking at a variety of antennas, starting with a monopole, you can see I've got a monopole right here, then inverted L, inverted F, and I eventually meander that. They're all going to have the same base circuit board, so it's best to define that as its own subcircuit. I've called that the feed subcircuit. That's going to have a transmission line feed. It's going to have some counterpoise material. The bottom side is going to be all ground plane. Top side is going to have some counterpoise material right below the antenna. Here's the edge of the board. So on this layer, I've had to draw the board. I've drawn a square of board material that's 80 by 40 millimeters. And then on top of that, I've just thrown a microstrip line element with 2.7 millimeters wide, and we've gone up 40 millimeters. And I've got another 8 millimeters of empty core material where the antenna element's going to go. So the antenna element will be driven at the end of the transmission line right here, and then connect back over to the ground plane as needed for the inverted F, or just come out for side wave. It's going to be the inverted L. And I've added vias in right here. Back on the piece of paper I was talking about the maximum, I guess the minimum electrical wavelength is going to be 22 millimeters. So I like to space my vias at a quarter electrical wavelength. Obviously, if they're half electrical wavelength, you're going to get substrate resonances. So we space these things at, right now they're spaced at 17, so that's slightly under quarter wavelength. So this is going to nail down this top metal, so it's not going to be able to resonate and establish modes within the circuit board. So it's also important to have good shielding up here. In reality, we could probably throw more vias in, but since the inverted F is going to be diverting some of his currents back to the ground plane, we need to be able to have a way for those currents to get back down to the main ground, which is carrying the microstrips return currents. So it's got to have good vias right here, and this is more for shielding once you get out to here. In reality, you would have circuitry on this board, so you're still going to want to have a little bit of shielding between your antenna element and the circuitry. So you notice this goes up right to the edge of the board right here. So port 2 will, be where we hook the antennas onto, and this is going to be instantiated into these other bunch of different antenna elements. So I brought up the monopole. Start simple. Start with the monopole. So that circuit consists of the feed circuit right here, and I've cascaded on a microstrip trace. And the reason why I want to use a trace is that we can go in and easily bend this thing to turn it into a inverted L. So you can see right now the trace is going off the substrate, but since we're going to be using Analyst, this substrate is going to be infinite, so this doesn't matter if it's going off the edge at all. And the length is parameterized, so I can take and change this length of the line. And when we instantiate this in an EM structure, we're going to be able to tune this thing. And the width, I've set this, instead of using this wide 2.7 millimeter wide 50 ohm line, we're going to set this to something that's more reasonable, 1 millimeter. It's going to be hard to pack this into a tight space or this wide. Once we get off we're not in microstrip anymore mode, once we get off into the substrate, so we can kind of set this to arbitrarily anything we want. Obviously the wider we make it, the better efficiency we're going to get probably, because we're not going to have as much current crowding on the line. And we may actually get a little more bandwidth too. If you expand the width of a monopole, you're gonna gain some bandwidth out of that. So so this is going to be instantiated into an EM test bench now. Now what I forgot to show when showing the feed was you can see I've got a solid copper piece of positive copper right here, and then the microstrip punches through the copper with the relief set by this width of negative copper. So it's essentially a coplanar waveguide. If I go back into, and I've got my, up here in the design notes, I've used transmit TX line to look at the proper width for microstrip. So 50 ohm microstrip line, 2.5 gigahertz, 2.69 millimeters wide. So we change that over to coplanar waveguide, set a gap of 1.5 millimeters. It's only decreasing by about 2 ohms. That's still going to give us a very good return loss. So we can punch through that counterpoise without affecting the impedance much at all. So, and we're going to have very tight return path then when we have our inverted F on here. So, but the way that's done is through a line type. If you go in that microstrip line and look at the excuse me, I need to go back over here in the layout and do it. Go to shape properties. Line type right here is called top. Top copper is the default. And now there's a top coplanar waveguide, which I've added. And that is under the layout process file. Excuse me, I need to go up here and say text edit process definition. So I've taken this top copper line type, and I've copied that and called it top CPWG, coplanar waveguide with ground. And I've added another layer under there called copper minus, and I've given an expansion of 0.0015 meters, since our units up here are in meters, length units. So it's going to expand. It's going to draw the same shape as copper. It doesn't have to be a straight microstrip. It could be a trace with bends and curves and all that fancy stuff, but it's going to take that copper and expand it on copper negative by 1.5 millimeters on either side of the trace. And when you save that process file and add the line type, now you can see it's automatically going to punch through that. So we don't need to do any kind of manual relief drawing in this thing. So I've created a EM structure. So when you create an EM structure, it's going to automatically grab a stack up. You got to tell it which stack up you want. So we've told it to grab the Axiem stack up sub 2. In this EM structure, I've called it _TB for test bench. So there's a couple different ways. There's probably about 4 ways of doing this, but if you're doing a circuit, you can use extraction. So you can draw your normal schematic layout, add an extraction block, and will automatically toss that artwork into an EM structure, simulate it, and push the results back. And those EM results now essentially overwrite your circuit results, and you can directly see your EM results within that schematic. For antennas, I typically like to use test benches because you're typically having to do a little bit better manipulation of the ports. With extraction, you can de-embed in reverse, but you can't de-embed forward on a transmission line. With a test bench, you can de-embed forward, and you can add on extra stuff. So what I've done, this is the schematic, the EM schematic. I've drug in the subcircuit from the monopole, and you can see the length right here. I can change that as needed. When I drug that in, it's going to stick it in. Here's into the EM structure. Here's the 3D view of it. So if you look at this port right here, I've gone ahead and added a port at the end of that microstrip line, and I've told it to de-embed all the way up to the edge of the ground plane. So our impedance is going to be referenced to this. The reference plane is going to be right here at the antenna element, not back here. But when I did that, I added a grounded port down to the bottom plane right here. And in order to do that properly, we need to add some ground plane on the backside, a few substrate lengths away, to take care of the currents that may be, at the outer edge of this port. And I've done that. And that's the advantage of the EM structure. You can bring your circuit in, and you can add on extra stuff as needed. Obviously, we don't want to manufacture this. We're going to want to put a edge mount SMA connector right here, flush with the edge of the board. But to simulate it with this ground strap port right here, we have to add this material. So I've manually added that into the EM structure. And it shouldn't affect the results very much. It's going to lengthen the ground plane slightly. But and then the other thing you have to do is I've got this SPPM, so that's a shape preprocessor. And in here I have rules for geometry creation. As I mentioned, inside the stack up, there's going to be rules for geometry simplification. But in here I have rules for geometry creation. So what I do is I need to, first thing I'm going to do is delete the board layers, because those aren't going to be used in Axiem. They could actually stay in there. It's not going to hurt anything since they're not mapped, but I like to delete them to get them out of the way. And then copper, we're going to subtract copper negative from copper plus and then stick it on the copper layer, and then delete those unused copper plus and minus, and do the same thing for copper too. And if you do it here in your SPPM element in the 3D view, it will show up as processed. If you could put these processing rules inside the EM structure inside the stack up, but the problem is if you do it there, it doesn't get done. It doesn't get processed until you run the simulation. So the copper negative subtraction from the copper plus is not going to show up. So you're not going to see your nice 3D view until you start to mesh it. Then you'll actually see the results. So I've gone ahead and simulated this. First thing, always look at the meshing. So if I take our 3D view and turn meshing on, you can see that if you zoom in here, you can see these vias are now turned into squares, and that's because of the geometry simplification rules I've put in there. And the mesh looks pretty good along the transmission line. We've got an edge mesh right here, and then a center mesh to capture the edge mesh. Obviously, if you look at the previous video I did, you need that to properly capture the edge currents because they're confined at the edges on microstrip. And then we don't have as good of a meshing on the antenna element, but that doesn't matter as much since we're essentially not a transmission line, we're a radiating element, so the edge currents aren't going to be as important. Now, we look at the return loss. I've added a marker here, a vertical line marker for 1575. So the goal is to, get a good return loss, 15, 20 dB. The return loss isn't, since this is going to be a receive antenna, we can trade off some bandwidth for return loss. This is looking like a monopole right here, at DC would start here at the open, we're going to curve around, we're going to hit resonance, and then curve back around to high impedance again, and eventually come over again when we hit the second resonance. But if you look at the locus on the Smith chart, ideally we want to move around and encompass the 50 ohm point. When we do that, we're going to get a little bit better bandwidth. We're going to trade some return loss off. If we go right through the center point, obviously we're going to get an infinitely negative return loss. But if we go to the outside right here versus kind of the inside, these points right here will be a little bit, be about the same distance away, but they'll be on the outside of it. And we're going to get a little bit wider bandwidth than if we had the locus, crossing on the higher impedance side of 50 ohms. So, but this is good enough for now. This shows that the monopole type response, has a good input impedance. So it has a length of 34. The ideal quarter wavelength in air is going to be 48. A quarter wavelength within a full substrate is going to be 22, but since we've got the filling factor on top of it, I adjusted this length until we got a very good return loss at 1575 megahertz. And then I've used markers right here. I've set this at a 10 dB return loss and added a delta marker over here, so delta 0 dB, so it's at the other 10 dB return loss on this side of the resonance. And it's 335 megahertz of bandwidth, and I had previously done the simulation and it had 338, but we'll change that to 335 megahertz. So I've already got these other values in here, but we're getting a very good bandwidth with this monopole, but the problem is it's taking up a huge amount of space. If you look at the Chu limit for antenna, or Chu's theory, it says that we want to maximize the volume, maximize the space. If you maximize the volume, you can get the best bandwidth, the best efficiency out of that by maximizing the volume. We don't really have a volume to work with here, but we have an area. So you can see we're getting very good bandwidth because we're taking up a lot of area right here. And it's really not just the physical area, it's the area for the reactive fields within here are taking up a lot of area. So as we decrease this, fold it over and start packing it in, we're going to lose bandwidth and we're going to lose efficiency. And then the efficiency, this efficiency includes the mismatch loss, the radiation losses from the real resistance in here. So we're almost at a 90% efficiency, which is negative 1 dB, slightly below that, but it's not bad. It looks pretty good. Now, looking at the current density animation, it's important when you do this to select, so Analyst is going to, it's going to interpolate between the frequencies it samples at, but the frequency it samples at, those are the only places you're going to be able to actually look at the current, unless you tell it to solve at every frequency in that list. That's going to take a long time. So if you look at the sampling frequencies, 1.58, that's very close to 1575 where our maximum return loss is. So it's important to choose this when you're looking at your current so that you're at a point of resonance and good return loss. But you can see that the currents are, concentrate at the edge of the microstrip line, but the monopole, this is a 10 dB scale. So you can see the currents are pretty strong at the base of the monopole, but up the edge here, there's not much current at all. But we're going to have a very high electric field off the edge here. So this also tells you, you're going to have a very low impedance if you're driving it right here, or moderate, I guess you could say, because we're shorter in a quarter wavelength, but we're at a 50 ohm impedance right now. But as you move up the line and get to the end, you're going to get to a very high impedance, and it kind of shows about what I was talking about, the inverted F. We want to raise the input impedance, the drive point impedance. We want to drive it up somewhere around this region right here. So now if I go back to the EM test bench, I can take and change this from a monopole over to the inverted L. And you can see that we've gone from the monopole, it automatically bended it around in parallel with the ground plane. So if I look at my inverted L schematic, it's essentially a duplicate of the monopole, except I've gone into this MC trace element and enabled the secondary fields right here. So when you take a MC trace, it starts off as straight. You can go into the layout and click the gravity points and start routing it to as many bends as you want, within certain restrictions of the line width. You can't get the bends too close to one another. But anyway, it's going to start populating this bend position array and bend angle array. Since we only have one bend in here, there's going to be one single element arrays, and this is going to be an angle of 270, and the distance is going to be measured from port 1 up to where the bend starts. So when I manually put this in here, this is 8 millimeters from the edge of the ground plane to the edge of the circuit board. When I manually drew this, it put the bend at 7 millimeters. So what I went back in and added a variable called dB for the position, and then I can take and manually change that. So if I open up the layout for this right here and change this parameter to, let's say, 12, it will put the bend higher up the length of the line, so you can parameterize that. I'll change that back to 7. And you can bring it all the way down to a value of 1, where it's just almost touching the line right here. But we'll go ahead and close this and get back to the EM schematic. So now this can be simulated, and it's not going to take very long at all to simulate. So now you can see that adding, what's going on there, it goes. The input impedance has gone from almost 50 ohms, now it's gone down to 16 ohms. And the return loss is poor now. Now it's about minus 6 dB, so we've lost probably a couple dB in gain of the antenna, since we're reflecting most of that power back. And of course we're also going to lose efficiency, and when we try to match this, we're going to lose bandwidth, because we've got to have that matching network in there. We're matching 50 ohms down to the 16 ohm impedance. So what I've done now is I've enabled this sweep variable. So you've got the dB variable up here, and we're going to step that from 34 millimeters down to 1 in steps of -3. So it's going to take and position the bend all the way up near the top and almost make this thing a monopole, then pull it all the way down to 1 millimeter, so it's going to stretch out right above the ground plane. And I've got to set the dB parameter in here to the variable dB. And when I do that, it's going to throw, you saw it sweep quickly geometry right here. It's going to throw in a bunch of 14 different simulations. It's going to kick off and populate the results for each step of in the downward direction of 3 millimeters. Now that simulation is done. It only took about 5 seconds per each of the 14 points. So you can look at the return loss at a bend position of 1, so we're almost touching the ground plane. It's pretty bad right here. It's like -1 dB. Of course, it gets very good as we go back down and extend this thing out to a monopole. Now, looking at the input impedance, I've set this input impedance, so instead of showing all the contours on here, or locus, I'm going to select each one with a tuner right here. So I'll go up to the tuner, and I've got the marker at 1575, and I can step through. So you can see with a bend position of 34, we're at the monopole. As we go back down, we're decreasing our input impedance. We started up at 53 ohms, and now we get down to like 9 ohms, 3 ohms. So you can see that pulling the inverted L down onto the ground plane really decreases our input impedance. Now we could possibly match that, but now we're going to be matching 5 ohms to 9 ohms. 50 ohms to 9 ohms, and that's really going to decrease our bandwidth that the antenna is going to operate over. What's happening is that, when this thing gets very close to the ground plane, we're forming a slot. And we've got an open-ended slot that is going to, say it's a quarter wavelength long. So you're going to get some odd effects right here where it's not going to exactly operate like you're not going to hit a short circuit immediately. You're going to get a slot mode being formed, and you could get a high impedance before you eventually collapse down to a short circuit. So it doesn't follow exactly the theory that was shown on paper, because we're forming a transmission line when this gets very close to the edge of the ground plane. So now I can go back and disable this and change this to the inverted F. And now you can see it's changed right here. Now if I go back into the inverted F schematic, what I've done right here, in fact, let me just open up, I'm going to close these out so we can get a better view of what's going on here. I'm going to open up the layout for that, and then window, tile, horizontal. So you can see I've got the original trace right here. And then what I've done is I've added another trace off to the side, and then another trace off to the top. And I've added a variable called feed offset. And I've set this to, this is 8 millimeters from right here up to the end of the bend right here, 8 millimeters in length. So I've added that variable feed offset. So as we increase the feed offset, it's going to shove this off to the left. And then the length right here, the original length, we want to keep the length from here to here the same as the monopole length. So over here I've subtracted the feed offset right here. So I've said take the original length and subtract the length of mtrace2.x1, which is the length of this right here. And then I've added a t in there, and we need to subtract the width of the t section right here. So I've told it to subtract the width of mtrace2.x2, so the width from right here. So by doing that, we're going to still get the same electrical length from the short circuit right here all the way up to the tip of the inverted L, same as the monopole length. But now we've got this feed right here, and that's going to be a length of 6.5, so it touches almost to the edge of the end of the substrate right here. And I've also parameterized the feed width. You'll see in a second that adding some inductance right here is going to improve the match. The feed width was originally 1, and by narrowing that up we can add some inductance and improve the impedance match. So now I've switched this over to the inverted F, and I've kept the length at 34 millimeters. And the feed offset, is 2.5 millimeters from here to here. So when you do that, you can see that this locus right here is an original monopole, and we went to the inverted F and our impedance decreased. But now, since we've moved the feed point up, instead of feeding it right here, we're feeding it right here, our impedance has increased. So now we're up to 197 ohms, but we really ought to be back about right here. The length is 34. We need to increase the length to move our resonance point, move the point so the resonance is right here. I had mentioned earlier there's two ways to think about this, as either moving the feed point up or adding a shunt inductance right here. This shows that the electrical length has decreased. We moved to a higher frequency because now we're feeding it right here. The monopole is sort of right here instead of right here, and we've added that inductance in parallel with it. So if I take and increase this to 37 and simulate it again, that's going to give us about the same locus and move us back to right here onto the real axis. So now that we're on the real axis, we've got a decent return loss, but we can do better. Adding some inductance, so increasing the inductance of the feed right here. So I change that width to 0.5 millimeters. That is going to help improve the return loss. And now you can see we're down at a 25 dB return loss, so we're very well matched. Now, take and change the offset. So we're at an offset of 2.5. Let's change this to an offset of 5. And you can see that it shifted over. We kept the same electrical length, but the entire thing shifted over, so we're feeding it at a higher impedance right now. Go ahead and simulate that and see what happens to the impedance. Now it's gone up. So now we're at 80 ohms resistance. And take and change that offset to 10. Now we're going higher, 132 ohms. And then go ahead and set it to, I think 20 is about the maximum. Maybe 25. 25, see what that is. And now you can see we're almost at an open right here. Very high impedance. Actually kind of forming a loop antenna. So set that back to 2.5. And get back to a decent impedance. So now the impedance is looking pretty good. The bandwidth has decreased. If I go to marker search and tell that to go to a Y value of -10, and we want to search right, and do the same thing for the delta marker, except search left. Now our bandwidth has collapsed to 134 megahertz. I think I had 136 megahertz written on here. So going from the monopole to the inverted F, we've lost, a good amount of bandwidth. We still got a pretty good return loss. And let's go back and take a look at the efficiency. Efficiency has gone down some. I don't remember what it was. Almost at -1. Now we're about -1.7. It looks like. So we've lost some efficiency and lost some bandwidth. But we're not at a giant monopole. We've collapsed this area that we have to work with. But we can do better. Now we've got this big section of transmission line off to the side. Let's see if we can collapse that down. As I had mentioned that most of the currents are confined within the first 2/3, so we should be able to meander this thing, and we can do what we want with this, as long as we don't add too much capacitive coupling, since it's a high voltage. As long as we don't add too much capacitive coupling back to the ground plane, we should be able to kind of meander this and reduce the size, and try to maintain a good input impedance while reducing the size. But again, we're going to probably lose bandwidth and lose efficiency in that process. So I take this inverted F and move it over to meandered F. So what I've done here, and let me go back and look at my parameters. So we need a length of 37, offset of 2.5, and a feed width. That's already baked into the circuit, is a feed width of 0.5. So let's go look at this meandered F schematic. Again, let me close these out so we get a better view. What I've done right here, and this needs to be snapped right there. That's one thing that you've got to do right here is in the layout options. Go up to where'd my layout options go? Auto snap on parameter changes. This defaults to manual snap. When you're doing parameterized artwork, you need to add this, turn this on, so when you do multiple simulations where you're varying a parameter, you want all this stuff to snap together. And that's where it's also important to take and freeze and use as anchors some of these artwork cells. So you want to be able to lock one thing into position and have everything else snap to it. And that's what this red and this blue thing are. That's set up back in the schematic for the circuit board, the feed board. So anyway, what I've done now is taken this same trace and then added meandering to it. So you can go through and, do this type of deal. And it's gonna, that doesn't look, but you get the picture. You can take and randomly add the bends to it. I can undo that right now and then snap it all together. So we want to be able to compact that in. And when we do that, you're going to get currents going up and down this direction, But on average, the current is still going to be moving in this direction because these currents are going to cancel. So you're going to still get a net current moving along the x-axis because the y ones are going to tend to cancel. And what I've done right here is I needed more inductance in that feed, so I meandered the feed now to add some inductance to improve the match. So I've gone ahead and simulated this. And the issue now is that this bend, it's set to the original length of 37. That's what the inverted F was at. But now the meandered F needs to be much longer electrically. So I've already got that figured out, and we're going to set it to 51. I set it back to 51. You're going to see those elements increase in size. The reason it has to be a lot longer is because we're coupling. So we're not really getting the electrical length that we think we have due to the coupling between the elements, but it's still going to be overall shorter than the inverted F was. I go back to inverted F. Actually, let me set this back to 30. Go back to inverted F. You can see I got to set this back to 34, 37 actually. It's going to be shorter. We're about right here with the meandered F. I go back to that meandered F. Set this length to 50, what is it, 51? Yeah, we're appreciably shorter, so now I'll go ahead and simulate that. And we're back to our original good impedance point. But now I've lost bandwidth again. If I do the marker search and search left, -10. Actually, search right, search left on that. We've collapsed to 86 megahertz of bandwidth. So look at the progression from the monopole. We've gone from 35 to 136 down to 87 megahertz of bandwidth. So losing bandwidth when we take and compact it. And the efficiency, we've lost some efficiency too. This efficiency looks kind of choppy because, again, the efficiency computation is using the sampling frequencies, which are only at these points right here. I could go back and tell Axiem to compute it at every frequency point which was selected. We get a much smoother efficiency curve, but it's going to take longer to do that. But I think that's at the point now where this can be transitioned over to a full 3D simulation to take into account the edge effects of the circuit board. So now I've got the Analyst test bench, which is very similar to the Axiem test bench, except I'm using the third stack up, where I had explicitly defined the substrate material in there. So now you can see that it's drawing the substrate. My boundary conditions, I've expanded these to 50 millimeters, again 1/4 wavelength on all three sides except for the bottom side right here. Since I want to de-embed from the port all the way to the feed point of the antenna, I'm using a wave port right here. And that's what you got to do to get the de-embedding. But I'm still far enough away, approximately 1/4 wavelength, that the near fields, at least for the antenna section, should be out of the away from the boundary condition. And I've also needed to modify the schematic preprocessor right here to add the rules to tell it to add the board back in. Otherwise, that's the only difference between the two is the boundary conditions. And the upper boundary conditions are obviously the same also. They're at 50,000. So now what I've done is I created a new element called meandered F3D. And that is showing up right here. And the reason I did that is because I needed to add more inductance. And you'll see a second in the simulation when I took and removed now we're on a finite substrate. We've got this edge effect right here. I've changed the capacitive reactance of this thing. Now it's seeing air instead of seeing a substrate. So I needed to increase the inductance on my match to get a good, to get a better impedance. So, And that's easier done by, if I went back and used my original meandered F subcircuit, I would have changed the Axiem simulation because I need to add more bends into it. So it's easier just to create a new copy, crop the subcircuit over, create a new one, and just add the increased number of bends in here. Now the analyst simulation setup. Go to options and look at the analyst options. I've told it to do all frequencies for the field output and all frequency for the field outputs and all frequencies for the antenna far fields, but I've also gone in and told it to do 3 iterations. Normally in the last video I talked about the 2% error from mesh iteration to iteration. I want to do 3 convergences below 2% in order to guarantee that my S parameters are essentially what they should be. So I've gone ahead and run this thing, and also what I've done back in the global definitions, I had core EVR defined here. Well, if I put that in, I substituted in the actual variables into this stack up. If I add that here, the local variable will override what is in the global definition. So I've gone ahead and set a core dielectric. I varied it from 4.0 to 5.0. Since this is, cruddy FR4, we really don't know what that dielectric is going to be. And I took and changed the length at the tip of this thing. So for 4.5, which is our nominal, it's going to be 51.6. But you can see for a higher dielectric constant, we need to shorten the thing because it has, more electrical delay in it. We need to shorten that line. For lower dielectric constant, we need to lengthen it. So we're going to be changing by about plus minus 1 millimeter from nominal to tune this thing on frequency. And also the bandwidth has decreased. So now, previously on the previous meandered F, it was 80 something megahertz, I think, and now it's back down. Now it's 47 by having putting a finite substrate in and increasing the inductance right here. So we lost some bandwidth, but we still have pretty good return loss. But I guess what you also got to realize is that when we're reducing bandwidth, we need to, unless you want to tune this thing for every everything that's done in production, you're going to have to make your bandwidth wide enough that it's going to encompass variations in your substrate. I think that I've never seen too much variations in decent, Rogers substrates. They're usually pretty tight. Once you get, even from lot to lot, they're pretty tight. But I've done some very thin antennas where I've looked at single lots, and try to buy material from the same lot to get that dialed in. But we can tune this, we can build this thing and tune it, and then go ahead and change the simulation to come back and see, adjust it to what we tuned it to in reality, and then see where it came up and then adjust the EVR to get that value that we had. So even though we're not going to directly measure the dielectric constant material, we can set it to the proper value that the simulation comes out to match the measured value. Now looking at the efficiency, the pink line right here is the final efficiency. We're about, we're not quite at -3, which is 50%. So we're probably somewhere around 60% or so efficiency, which is, typically what you're going to get with these type of antennas. Now looking at the gain, I close that and open up a new 3D view. Actually, this is going to be the current. Let's look at the currents on the thing. And let me go back and make sure that we're on 1575 for the currents. So go and animate that. You can see that, again, most of the currents are confined to the first 2/3 of the transmission line. You have to be very careful about where you position this final trace right here. If you get it too close to the ground plane, you've got a very high voltage, so the capacitance is going to more greatly affect the resonance than it would from down here where we have a high current. So sometimes it's best to position it so it's kind of in the middle, so when you do change the length, it doesn't change the capacitance as much between the edge here and the edge on the ground plane. You also see a little bit of a phase delay between the inductor and the currents right on here, but it's not as much as it was in the previous inverted F that didn't have the smaller inductance right there. So now I can go ahead and I've got the pattern defined. Let me open up a new window here. There we go. Now you can see that the pattern is, and this is the actual realized gain, so it takes into account the mismatch loss. Not that there isn't much in 1575, but we're about 3.4 dBi of gain, and this is not any set polarization. This is just the total gain for all polarization. So this is for again, I mentioned it was for GPS. So yeah, ideally in GPS you want to have good right-hand circular polarization and an antenna pattern looking up at the sky. But in, let's say, handheld devices, let's say a phone, you're going to have a random orientation. So the metric you really want to look at is efficiency more so than polarization, because you can't control the polarization, you can't control the orientation of the phone. So you want to try to maximize the efficiency rather than try to throw away something to try to maximize again, polarization, orientation, which you really can't control. So now, in order to manufacture this thing, I can go back in here and I've created a new schematic called GNSS Inverted F Antenna Revision 0. And in that I've placed the meandered F. And I've set these lengths and offset to the nominal for the e to the r of 4.5. And I open that up. I've also taken and added in some notes on here, on the notes layer, saying what my copper is and my core material. I already got this, so this is going to be built on the milling machine. But if we were to manufacture this at a board fab, we'd want to add all the notes in here, and no solder mask, no overlay. There's no edge relief between the edge of the board and the metallization. Normally I add 0.2 millimeters, but I don't really care if this cuts right across the copper. This is just for a prototype. So going and look at the drawing layers and look at the export, Gerber export, we only want to export copper, copper 2, board, and notes. And now if I go up here and say scripts, layout, export PCB drill Gerber, I'm going to tell it to take the shapes on the via layer and turn those into a drill file, all in one file. You could change this if you had multiple size shapes. And then we want to use this layout right here, put it in metric and click OK, give it a directory to export, and we'll go through and export those files. Now I've got Altium opened up, so I can do create a new CAM document and say File, Import, Quick Load, and let's just select all the files. We're going to start, default units. We're going to go with 4.3 metric. Okay, and it's going to suck this stuff in. Drill units. I think there's a bug in this version of Altium. It should be 4.3 metric. I go back here, and it actually, no, it did work. There's not a bug. So now you can see if I go back through the layers, turn all these off, set my board layer, turn that on. There's a board outline. There's the copper for the top. Copper 2 is taking up that section, for the ground underneath there. And then my notes, drill holes. So it's all there, so it's ready to be sent off to the board house.